Weak acids are things that are not on this list. And when they dissociate, they don't dissociate completely. They dissociate in an equilibrium. We're going to call these weak acids HA. So the proton A and some anion A minus. So anything that's not on that list is a weak acid. Now, when we look at this, we identify stronger conjugate acids and bases and weaker acids and bases within a particular reaction. So if here we have acetic acid reacting with water to make hydronium and acetate. So acetic acid is the acid. Its conjugate base is the acetate ion. Water is acting as a base. Its conjugate acid is the hydronium ion. So when we look at this, you say, okay, I have one acid and one base, and then I have their conjugate acid and base on the other side. So if we know that the position of the equilibrium will rest favoring the weaker conjugates. Now, when you think about this, I think of it as the stronger acid wins. So the strong acid-base pair react, they get used up, and you make the weak ones. That's how I think of it, and that's how I was able to remember it. The stronger ones are going to react and go in that direction. So if the hydronium ion is the stronger acid, so if this is the stronger side, then it's going to push the equilibrium to the left, so it will favor the reactant side. So this would be reactant favored. I just told you. Okay, for now, I just told you. Later on, we'll look at the equilibrium constants, and that will tell us. Okay, so for this one, looking at this one, I'm telling you, acetic acid is stronger acid than the hydrogen sulfide ion. So what will the position of this equilibrium be? Reactant or product favored? Reactant favored. And how about the last one? If the hydrogen sulfate is a stronger ion or stronger acid than the hydrogen phosphate ion? Product favored. So the stronger ones will react and push the equilibrium in the opposite direction. Now, what's on the next page is just some information about acids and bases that is not particularly critical for us in this class, but it is stuff that can appear on the final, and it is things that will pop up occasionally when you're trying to think about stronger and weaker, but this is not as super high in importance. So when we have binary acids where we have things like hydrochloric, hydrosulfuric, that kind of acid, as we're looking at the periodic chart, they increase in strength from left to right in a period and from top to bottom in a group. So if you think about putting this arrows on the periodic chart, look at the second period going left to right for boron, carbon, nitrogen. So hydronitric acid would be a stronger acid than hydrocarbonic acid. And if we look in a group, hydrogen iodide or hydroiodic acid would be a stronger acid than hydrofluoric acid, which is at the top of the chart. Now, if you're trying to remember these trends, the way that I always remembered was to look at the chart, because if you think about the halogens, hydrochloric, hydrobromic, hydroiodic are all strong acids, and hydrofluoric is a weak acid. So when I look at the way they're stacked up in the chart with fluorine on the top, that makes sense to me that the trend goes down. Okay, because you look at it and you've got fluorine, chlorine, bromine, iodine in that trend, and so that kind of helps me. And then the way I was able to remember going left to right is the halogens so many of the halogens are strong acids that it made sense going over towards that you'd get strong acids on the right. And remember, the whole noble gas thing is kind of excluded because we don't make acids out of the noble gases. That sounded nasty too. All right, so now let's look at the oxoacids. When we think about oxoacids, we have two factors. Strength is affected by the number of oxygen atoms and by the electronegativity of the central atom. If you have the same central atom, then more oxygen makes for a stronger acid. So the ic acid is always stronger than the us acid. So say sulfuric acid will be stronger than sulfurous acid. Or carbonic acid will be stronger than carbonous acid. Now, when you have the same number of oxygens, now you can look at the electronegativity of the central atom, and these increase in strength from left to right across a period and from bottom to top. So this is a different trend than those for the binary acids. So we can have then sulfuric acid would be stronger than phosphoric acid, because if we're looking at those on the periodic chart, phosphorus and sulfur are in the same period and sulfur is further right. And perchloric acid would be stronger than periodic acid. And again, this one I can help remember the trend because perchloric acid is one of the strong acids and periodic acid is a weak acid. So that goes from the bottom to top trend. Okay, so the next general topic in acid-base is just a quick revisit of the definition of Lewis acids and bases. This was introduced in Chem 111 when you studied Lewis structures, and we talked about the formation of a coordinate covalent bond. In the Lewis acid base, you don't need water, and you don't even need hydrogen ions. We talk about electrons. In the Lewis acid, it is something that can accept a pair of electrons because it has a non-filled or insufficient octet. And a Lewis base is an electron pair donor because it has a full octet. So we talk about neutralization as the formation of a coordinate covalent bond. So if we think about this, remember nitrogen has that lone pair in ammonia. You have a proton with no electrons, and these can combine and make the ammonium ion, which now has no lone pair because you made this bond. So this is the base, it's donating the electrons, and this is the acid, it's accepting the electrons. So that's sort of the definition stuff in acids. Now, the other thing that we're not going to talk about very much, but I mentioned because you take a standardized 2-semester final in here. And I mention it because this may appear on the final, even though we're not going to deal with it too much in here. When we start talking about metal ions in solution later in Chapter 16, we are going to assume that all the metal ions we're dealing with have no acid-base behavior. Okay, so you might want to make a note of that just for yourself as you're studying, that for our purposes in this class, we're not going to deal with metals that act like acids or bases. But some metals can. And so you can have some metal, M, that has a positive charge, a metal cation, reacting with water, and you make this complex ion, where you have a hydrated metal ion that has the same charge as the metal. The hydrated ion can then act like an acid and set up an equilibrium in the water. So you have this hydrated metal ion, and it's got some charge, whatever the charge was on the metal. It can now react with water doing acid-base chemistry to make a metal hydroxide. The charge is now N minus 1 because you lost one proton, plus you make a hydronium ion. And this is some chemistry that can happen. You might see one question about this on the final, but we're not going to spend a lot of time on it. And the periodic table can help us predict this because it depends on the density of the ion. So small cations will be the most acidic when they have big charges. So if you're looking at the periodic chart, remember, down here, things are big, and up here in the right corner, things are small. So things up in this area will tend to be the more acidic metals. And aluminum can do this chemistry. It's one of the most well-known, but we're not going to fuss with it too much. Okay, then the last thing, and just some general acid-base chemistry, that when you start thinking about this in Chapter 16, if we have oxides, salts that contain the oxide ion, O2-, metal oxides will react with water and form bases. So something like sodium oxide will react with water, and it makes sodium hydroxide in equilibrium. If we have, say, calcium oxide, this can also react with water and make calcium hydroxide. And again, this is nothing new. This was introduced in Chem 111, but it's not super important for us. But you need to understand that this will then make an acid or a base solution, which we talk about in Chapter 16. And nonmetal oxides, like sulfur trioxide, can react with water and make sulfuric acid. Sulfur dioxide, you might know this from environmental concerns, reacts with water and it makes sulfurous acid. This is acid rain. And another example, carbon dioxide, like what's in my Diet Coke here, reacts with water and makes carbonic acid. What I use to get my morning started every day. Okay, so that kind of wraps up the reintroduction to acid-base chemistry.